Welcome to Section 6, Lesson 3. In the previous lesson, we covered substitution, the first algebraic method for solving linear systems. Today, we cover the second algebraic method, elimination. Elimination adds or subtracts multiples of the two equations to cancel one of the two variables, reducing the system to a one-variable equation that the Section 3 machinery handles directly. Elimination is often faster than substitution when both variables have integer coefficients greater than 1 because it avoids the fraction handling that substitution often forces. Today we lock in the four-step elimination procedure and walk through two examples illustrating direct cancellation and the multiply first variant. First idea on the board. Elimination uses the balance principle from Section 3 applied across two equations. Adding the left sides of two equations and adding the right sides produces a new equation that is satisfied by the same x and y values that satisfy both originals. Similarly for subtraction, by choosing how to combine the equations, we can produce a new equation in which one of the variables has coefficient 0, eliminating that variable and leaving an equation in the other variable alone. The eliminated variable can then be recovered by back substitution, exactly as in the substitution method. Second idea. The four-step elimination procedure is Step 1. Align the equations vertically with like terms in columns. Step 2. Multiply one or both equations by suitable constants if necessary so that the coefficients of one variable are equal in magnitude and opposite or same in sign for the cancellation to work. Step 3. Add or subtract the equations to cancel that variable, producing a one-variable equation. Step 4. Solve the one-variable equation and back substitute into either original equation to find the other variable. Verify both values in both originals. Third idea. The choice of which variable to eliminate depends on the coefficients in the two equations. Look for a variable that already has the same coefficient or opposite coefficients across the two equations. That variable can be cancelled directly by subtraction or addition. If no variable has matching coefficients, multiply one or both equations by suitable constants to make the coefficients align. The strategic choice does not affect correctness but reduces the algebra burden. Today's first example illustrates direct cancellation. The second illustrates the multiply first variant where we have to align coefficients before cancelling. Elimination adds or subtracts multiples of the two equations in a system to cancel one of the two variables. The cancellation reduces the two-variable system to a one-variable equation, which the Section 3 inverse operation machinery solves directly. The eliminated variable is recovered by back substituting the solved value into either original equation. Here is the four-step procedure. Step 1 is align. Write the two equations vertically with the x terms above each other, the y terms above each other, the constants on the right. The visual alignment makes the next steps easier to track. Step 2 is multiply. Multiply one or both equations by suitable constants to make the coefficient of the variable you want to eliminate match in magnitude across the two equations. If the coefficients are already equal or opposite, you can skip this step. The multiplication uses the balance principle from Section 3. Multiplying both sides of an equation by the same non-zero constant produces an equivalent equation with the same solutions. Step 3 is combine. Add the two equations if the coefficients are opposite. Subtract one equation from the other if the coefficients are equal. The targeted variable cancels, leaving an equation in the other variable only. Step 4 is solve and back substitute. Solve the one-variable equation using inverse operations. Plug the solved value into either original equation and solve for the other variable. Verify both values in both original equations. The procedure produces exact answers reliably regardless of the specific numerical values, just like substitution, but often with less algebraic burden when both variables have integer coefficients greater than 1. Here is the first worked example. Solve the system 2x plus 3y equals 12 paired with 4x minus 3y equals 6 using the elimination method. The y coefficients are plus 3 and minus 3, exactly opposite, so direct addition will cancel the y variable without any preliminary multiplication. Step 1. Align the equations vertically. 2x plus 3y equals 12 on top, 4x minus 3y equals 6 below. The x terms are stacked, the y terms are stacked, the constants on the right are stacked. Step 2. Check coefficients. The y coefficients are plus 3 and minus 3, exactly opposite. Direct addition will cancel the y, no multiplication step needed. Step 3. Add the two equations. Left side's 2x plus 3y plus 4x minus 3y equals 6x. Right side's 12 plus 6 equals 18. So the combined equation is 6x equals 18. Step 4. Solve for x. Divide both sides by 6x equals 3. Step 5. Back substitute x equals 3 into either original equation. Use the first 2 times 3 plus 3y equals 12. 6 plus 3y equals 12. Subtract 6 3y equals 6. Divide by 3y equals 2. Step 6. Verify in both originals. First equation 2 times 3 plus 3 times 2 equals 6 plus 6 equals 12 match. Second equation 4 times 3 minus 3 times 2 equals 12 minus 6 equals 6 match. Solution verified. So the solution is x equals 3 and y equals 2. The big lesson from this example is the direct cancellation case where opposite coefficients on one variable across the two equations. Let us add the equations and eliminate that variable without any preliminary multiplication. Direct cancellation is the cleanest case of elimination and is recognizable from the equation form by inspection. Always scan the two equations for opposite or equal coefficients before doing any other work. If you find them, direct elimination is one step away. Here is the second worked example. Solve the system 3x plus 5y equals 11 paired with 2x plus 4y equals 8 using the elimination method. The coefficients do not match directly, so we will multiply the equations to align them before cancellation. Step 1. Align the equations. 3x plus 5y equals 11 on top, 2x plus 4y equals 8 below. We need to choose which variable to eliminate by multiplication. Step 2. Choose the variable. Eliminate x by multiplying the first equation by 2 and the second equation by 3. Then both equations will have x coefficient 6 and subtraction will cancel the x. The first equation times 2 6x plus 10y equals 22. The second equation times 3 6x plus 12y equals 24. Both x coefficients are now 6. Step 4. Subtract the first new equation from the second new equation. Left side 6x plus 12y minus the quantity 6x plus 10y equals 2y. Right side's 24 minus 22 equals 2. The combined equation is 2y equals 2, so y equals 1. Back substitute y equals 1 into either original equation. Use the second 2x plus 4 times 1 equals 8. 2x plus 4 equals 8. Subtract 4, 2x equals 4. Divide by 2x equals 2. Step 6. Verify in both originals. First equation 3 times 2 plus 5 times 1 equals 6 plus 5 equals 11. Match. Second equation 2 times 2 plus 4 times 1 equals 4 plus 4 equals 8. Match. Solution verified. So the solution is x equals 2 and y equals 1. The big lesson from this example is the multiply first variant of elimination, where we need to scale the equations before cancellation can run. The choice of multiplication factors depends on the target coefficient. Any common multiple of the two existing coefficients works, with the smallest common multiple producing the cleanest algebra. The procedure is mechanical once the multiplication step is in place, and elimination is often faster than substitution for systems with integer coefficients greater than 1 because it avoids the fraction handling that substitution forces in those systems. 3 mistakes that catch every algebra student during their first weeks of elimination work. Each one is fixable with a small explicit habit applied on every problem. First mistake. Sign error during subtraction, especially when subtracting an equation with multiple terms on the right side. A student subtracting 2x plus 4y equals 8 from 6x plus 12y equals 24 writes the right side as 24 minus 8 equals 16, but the left side as 4x plus 8, due to a sign error on the y subtraction, getting 4x plus 8y equals 16 instead of the correct 4x plus 8y equals 16. Wait, that example is correct. Let me restate. The error pattern is subtracting 24 minus 8 gives 16, but a student writes minus 16 by sign, flipping mistakenly. The fix is to always write the subtraction step explicitly with the second equation flipped to addition form. Subtract is add the negative. Use the explicit form to keep signs clean. Second mistake, multiplying only one side of an equation when scaling it for elimination. A student wanting to multiply the first equation by 2 writes 6x plus 10y equals 11, missing that the right side 11 also gets multiplied by 2 to give 22. The fix is to remember that multiplication by a constant is an operation on both sides of the equation, exactly as the section 3 balance principle requires. Always multiply through every term on both sides, not just the variable terms on the left. Third mistake, solving for one variable and stopping without back substituting for the other. A student finds x equals 3 after the elimination step and declares that as the answer, missing that the system's solution requires both x and y values. The fix is the same as in the substitution lesson. Always remember the system has two variables, and the back substitution step is mandatory. Plug the solved value into either original equation and solve for the other variable before stating the final answer. Elimination is the workhorse algebraic technique for systems with integer coefficients greater than 1 and is the foundational method that scales into the full machinery of linear algebra. 4 broad sectors below. In physics, the equilibrium of an object under multiple forces produces a system of equations expressing that the net force in each spatial direction is 0. Each force component contributes a term to each equation, and elimination solves for the unknown forces or accelerations. Statics analysis of bridges, beams, and trusses all rely on systems solved by elimination. The method scales naturally to three-dimensional equilibrium with three-component equations and the corresponding unknowns. In chemistry and pharmacy, mixture problems where two solutions are combined to produce a target concentration produce a system of two equations, one for the total volume of the mixture, one for the conservation of a specific solute. Elimination cancels one variable cleanly when the coefficients align nicely, often the case in standard mixture problems. The technique is foundational across chemistry lab work and pharmaceutical compounding. In electrical engineering, Kirchhoff's current law and Kirchhoff's voltage law applied to a circuit produce a system of linear equations relating the unknown branch currents and node voltages to the known sources and resistances. The system is typically solved by elimination or by the equivalent matrix method. Every electrical engineer doing circuit analysis uses elimination-based system solving as a fundamental tool, often automated by simulation software, but built on the same algorithmic foundation. In linear algebra, Gaussian elimination is the algorithmic generalization of the elimination method to systems with many variables and many equations. The textbook procedure scales the manual elimination workflow you learned today to systems with hundreds or thousands of variables, executed by computer software. Mastering the manual elimination method now is the literal foundation for understanding Gaussian elimination and matrix-based system solving in later courses, including the linear algebra and numerical analysis courses you may take in college. 3 things to take with you from this lesson today. Elimination is the second main algebraic method for solving linear systems, complementing the substitution method from the previous lesson. And together the two methods cover every standard linear system you will encounter for the rest of the algebra course and into the linear algebra material in later courses you may take. First, the four-step elimination procedure is align, multiply if necessary, add or subtract to cancel one variable, then solve and back substitute for the second variable. Align the two equations vertically with like terms in columns. Multiply one or both equations by suitable constants to align the coefficients of the variable you want to eliminate. Add the equations if the coefficients are opposite. Subtract one equation from the other if they are equal. Solve the resulting one variable equation and back substitute into either original equation to find the other variable. Second, elimination is often the faster of the two methods for systems with integer coefficients greater than 1 because it avoids the fraction handling that substitution forces in those particular systems. The choice between the two methods depends on the form of the equation. Substitution shines when one variable has coefficient plus or minus 1 in either of the equations, while elimination shines when both equations have integer coefficients greater than 1 with the variable coefficients aligning nicely or aligning easily through multiplication. The next lesson covers how to choose the right method explicitly. Third, two craft details prevent the most common elimination errors. When multiplying an equation by a constant, multiply every term on both sides of the equation, not just the variable terms on the left side of the equation. The constant on the right side also gets multiplied by the same factor, exactly as the Section 3 balance principle for equation manipulation requires. And after solving for one variable through elimination, always back substitute into either of the two original equations to find the other variable. The solution requires both values, not just one. Verify both values in both original equations as a final check. The verification step also confirms that the algebraic manipulations were performed correctly because both equations of the original system must hold for the solution to count as valid. Elimination is one of the foundational techniques in all of linear algebra, and mastering it now sets up the matrix-based system solving methods you will encounter in higher math classes. The Gaussian elimination algorithm used by computer software to solve large linear systems is a direct generalization of the manual elimination procedure you learned today, scaled up to many variables and many equations through systematic row operations on the matrix of coefficients. Recognizing that mental connection helps the matrix methods feel natural when you encounter them later. Coming up next, the lesson called Choosing the Right Method, where we compare substitution, elimination, and the graphical method side by side and develop a decision rule for picking the most efficient method on any given linear system. The choice of method does not affect correctness, but can dramatically reduce the algebra burden, and recognizing the right method on each problem is the central craft skill of efficient system solving for the rest of the algebra course.